Welcome in. Proving the chain rule, okay, so for derivatives in calculus when you're beginning is not the easiest thing to do. And I'm going to try to break it down for you. So this may not be the most ideal proof, but it hopefully will give you some kind of a sense why the chain rule works. Now, what is the chain rule? So first of all, it is a matter of working with composite functions. And typically you assume that there's two functions, but of course there can be many more. So you can extend the chain rule as much as you like. So I'm going to stick just to the general case, which is just one function, okay, going into another one. So you have an input, and that input is being fed into a function. So this function we're going to assume is differentiable. So the derivative of this exists, and that gives us an output. Okay, so let's assume that it is u. So I'm going to just write here so that u is equal to f at x. And now that output of that first function is now fed into the second function, so that g that you see there. So now g's input is the actual u. But if we would compose and bring everything together, then really what we would have is we would have that y is equal to, this would have been g, we would have substituted the u inside of there, so that would have been f at x, and that would have been our composite functions. Now very often you might also see this as being written out in a particular order with this little kind of circle, okay, that you have. So it might look something like this. So I'm going to try to stick to this notation for us in order to try to figure out what the chain rule is. So again, I mentioned that I'm going to assume that f is differentiable. And if it's differentiable, then its derivative actually exists. And then I'm going to also assume that g is differentiable. So both of these actually have a derivative. Okay, so I'm not being worried or preoccupied with the derivatives actually existing or not. So I'm going to assume that they do exist. Now, the chain rule says the following, that if you wanted to take the derivative of our output, so dy, with respect to dx, okay, so with this original input x, which of course can be just simply written as y prime, depending on which notation you're using, this is equal to the derivative of g, okay, so that's what it would have been right there, where we keep fx as our input, okay, and it's kept constant, and then it is being multiplied by the derivative of our original function f. That's what the chain rule actually states, and it is super nice to be able to use because it provides us a nice and easy way of decomposing derivatives from various functions. So why is this the case? Okay, so I'm going to try to reverse engineer the actual proof, and hopefully you will find value in that so that you can kind of think, and it'll be another way of trying to approach proofs in general. So I'm going to go from my result. So this is my actual result. Now I'm going to write this result in the following way. So this is going to be g prime, okay, of u, because that's what f at x, I have defined it right there, and then multiplied by f, okay, sorry, the derivative of f, okay, with respect to x. Now, of course, the whole function is with respect to x because that is our actual input that we see right there, okay? And so it's just being chained along the way. Okay, so if that is the case, so reverse engineering this, okay, it's going to take a little bit of work. Now, before I begin, I would want you, because it's going to be something that we'll need, I will want you to kind of think about the following. So I'm going to define for us, so let's say, as we use h, right, so as h tends towards 0, we like to define the actual full derivative with respect to this, this h variable as it tends and gets smaller and smaller and smaller. Now, I'm going to take an h, but with respect to, you know, this function g, so it still tends towards 0, and I'm going to define it in a very odd way, you might think. Okay, so this is going to be defined as f x plus h minus f x. Okay, so it looks like something that I have a difference with respect to that second derivative of the function f, which is my initial function. So now, why am I going to be defining it like this? You'll hopefully see shortly in this reverse engineered way of this proof. And I also want you to realize that if I would say, okay, and if I take the limit as hg, okay, is approaching to 0, as this is approaching to 0, then, okay, hopefully you can see that this implies that that's the same thing as basically saying that this entire thing is approaching to 0. Now, when does this approach 0? Because our x is just our input, right? So really the only thing, okay, is h, which is what's tending here. So these two things, it's like saying that this is having h approach to 0, okay, with respect to this fx plus h minus fx. So if I would write the limit, okay, of hg is approaching to 0, that's the same thing as saying that it is the limit as h approaches to 0 of this. Okay, so I hope that you can see that. So what I mean is this: if the limit, okay, if I'm writing this of hg is approaching to 0, so that means this is approaching to 0, this is the same thing as saying that the limit of h approaches to 0 for this fx plus h minus fx. Okay? So these are kind of preliminary items that I'm going to be thinking about. So I want you to, you know, keep this in mind, this hg. Okay, so coming back to here. So this is what I am after. So let me duplicate and bring it down right here. And now in terms of reverse engineering, okay, so here it is. So I'm going to first, and maybe I'll separate it. So I'll take this initially, okay? What would this mean? Now this is with respect to this u right here in the moment, although we know that u is just simply f at x. So if I would write out the original limit, okay, I'm going to write it like this. I'm going to say limit as hg is approaching to 0, okay? And now this is going to be g u plus hg minus g, okay, at u all over, okay, hg. Now, of course, if I would drop the g entirely, then you would have been used to seeing this, and you would say, oh, that's just the derivative, okay, of g, which is exactly what we want, right? So we're reverse engineering. So this is, okay, what this actually means. Now, okay, let me make this a little bit smaller so that I have room for my second one. So here is my f, okay? So it's multiplied by. So this is multiplied by. And now if I would write this, this would have been limit. And here I will keep my h, okay, approaches to 0. And this is going to be f, x plus h minus fx all over h. So that's what I have right there, and this is just basically the definition of this, right? So that's just the derivative. So I have the two derivatives being multiplied together. Now you might say, okay, so that's nice. Now how is this going to lead to a particular proof? Okay, so I am going backwards, okay, in this proof. So I'm reverse engineering the actual proof because I'm trying to figure out, okay, how to make this work. Now, okay, what I would want you to see in here, so for the moment, okay, these particular limits, okay, so this limit right here, okay, and then I have this limit right here. Okay, so those are the two limits that I actually have. Let me just kind of remove them, all right? So entirely. So I'm going to put them away. So here is my first one. Okay, I'm going to duplicate it. So I'm going to put it here on the side. Okay, and then here's my second one. Okay, so this one, okay, I'm going to duplicate it and I'm going to just kind of remove it. So I know that these limits are there. And now what I have is, I have this, okay, right here. So I'm going to duplicate it. I'm going to bring it down as so. And then I have this, okay, so which is being multiplied throughout. So this is, multiplied by that. So here's the multiplication. Okay, so if I have this, okay, where those limits are kind of dropped, notice that within here, what I'm going to do is, okay, I'm going to just swap these, okay, so I'm going to take this, and I'm going to swap it with the h over here, okay, so I'm going to swap those. Okay, so because it's just multiplication, that isn't really a worry for me. So this is going to be over here, and this is going to be over here, right? So this is what I have. Okay, so far I've just kind of swapped those two. Now, I do know what hg actually is, right? So this particular hg I have defined to be, okay, so if I go back in here, so, I said that is what hg is. So hg is just all of that. So now, if I change this, okay, so throughout, let me just concentrate on this for the moment. So let me duplicate it. I'll bring it down over here. So this hg is nothing else but simply fx plus h minus fx. Okay, so that's what that would be. Now, my u, okay, so that I have in here, okay, so this particular u, notice, okay, that I have that in there. And I also have this hg in here as well. Now, what was u and then what was hg? Well, u is nothing else, but as you can see here, okay, so if I go back in, okay, this was what u was. It was just fx. So if I substitute that back in here, so then what I'm going to get is I'm going to get g, and this is going to be fx plus, now hg right there was nothing else but simply, okay, all of this, all right? So I'm going to duplicate it and bring it down here. So that's what this is. So that is my u and my hg minus, okay, that g, and then u was just fx, okay? But hold on a second. So fx minus fx, okay, so this is now g of fx plus h in here, that's what I have right there, minus g of fx over here, and I still have that h, right? So I can't forget, okay, I still have that h there, so that would have been my h over here. And so now within, now of course, okay, I have done this entire thing right there. So bringing it all together, so that's that piece plus this piece over here. Well, but this piece, hold on a second, that's just 1, no matter what that is. Although it is hg, right, as I've defined it. So hg over hg will just cancel, and it's going to give me 1. Okay, so what I have in here is the following. Now I still have these limits, okay, over here. So let me go back in here. Okay, and let me duplicate these limits, bring it down just so that you can see what's happening. So this is what I have, okay? Okay, this entire thing. So this is, let me just make it smaller. So let me do that. So I have all of this right there. And this is supposed to be multiplying. So it's supposed to be multiplying, all right, this thing right here. Okay, so I'm going to duplicate this right there. We're going to change the color, okay, to purple so that you can see that. Okay, let me bring that down. So this is what you have over there. And now, okay, so if I go back in here, so this is basically nothing else but simply hg, because that's how hg was defined, divided by hg, correct? Now that limit, okay, of that hg, if I duplicate it, okay, so bring it within here, this over here, as you can see, so hg is never actually 0, right? It tends towards 0. That's the limit properties that we have. So ultimately, you know, so this, I'm going to duplicate it over here, so hopefully you can see. So this is just simply hg over hg, which is just the limit of hg approaching to 0 of 1, which is a constant. And the limit, okay, of a constant is of course just, okay, the constant itself. So that's just 1. So now we have 1 multiplying all of this over here, which is going to be our answer, right? So this multiplied by 1, I'm going to duplicate it, bring it over here, make it bigger, is basically our entire answer. But hold on a second. What is this? This is the definition of our derivative of the function. So this entire thing is the definition of the derivative of our function. And our function was g f at x, okay? Sorry, g at f, and f is at x, okay? So this is what we were looking for. So that is the derivative of that. So I have now reversed engineer the actual proof. So now if you go backwards, okay, you're going to get your result. So you would start with the actual proof, okay? You can define this right here. So as limit hg is approaching to 0, okay, of a constant, okay, so meaning really we're multiplying by the numerator and denominator. So we're just multiplying the numerator and denominator by this. Then what we're doing is we're taking this right here and this h and swapping them. So that's what you see happening right here. So this will swap with this. Okay, so that's going to swap over. So that's what you see here. That is now that within here. We know what u is, u, okay, in terms of its definition. So we can see that, okay, within here. So that's going to be, so that's our u over here. So we would define, okay, that. And it will finally lead us to this. So that is the proof which is in reverse. Okay? So you can basically stop here if you have understood this entire proof. Okay? Because that is all that you would have. You would just have to now go backwards. Now, that would have been very hard to do, to start from the beginning. However, if you can see the reverse engineering of the proof, then hopefully that will help you. I don't know if I've done, a good enough job. Hopefully, okay, it may help some of you, and I definitely welcome any comments from those, okay, who are interested in doing this, okay, in reverse. And then, of course, you can start from here, do your definitions, okay, and then head backwards to actually get your derivative. Thanks for watching. We'll see you in a future video. Happy studying calculus, folks. Bye, everybody.